Today we're going to look at the applications then, and before we start, one of the things that, I don't know why, it's because there's a pi in there, but it tends to throw people off. So all we want to do is just practice this first. If you saw this kind of equation, and that was the horizontal stretch that I was going to use or apply to it, then if I want to find out the period, in this case it would be 2 pi divided by 2 pi over 3. So does anybody know how to work that fraction out? Yeah, it's going to end up being 3. If you're not like a super fraction whiz, you will be by the time we finish the next unit. But you can probably get away with it for one more unit. We'll do it again over here. This would be 2 pi over 5. And this time the period would be, yeah. So the point of this is we're going to try and fit this trig data. Like we're going to have some data, we're going to try and fit it to a trig equation. So if you know you want like a period of say, I don't know, 131, you could go like this and use 2 pi over 131, and that way you know the graph has a period of 131. Okay? So if you want a given period and that is going to be p, what you do is you stick it into the equation like that. Now another thing for convenience, and it's super worth it for you to know these 4 pictures. For example, if you're given some information and it tells you about the problem and it's starting at its highest point, right? That means that it's going to go like this. If it's a trig graph that starts at its highest point, it's going to look something like that. So which graph, what would you call that? Yeah, that looks a lot like cosine. But what if I told you some information and what you got started at the minimum instead? What do you think of this? Yeah, it looks like a negative cosine graph. It's the cosine graph flipped upside down. So the reason that this is going to be, you know, if you line up the information you have, you're going to spend less time looking around trying to line it up in the equation. Generally, it's the phase shift that's easiest to do if you use this, you know, separating between cosine, negative cosine. We might have something like it's at the middle and it starts rising. Let me shrink that so it fits on the same graph. Something like that. And you recognize that as, yeah, that's your sine graph. So I guess I don't even need to ask the last one. Process of elimination, you can probably figure it out. This is the negative sine of x. Starts at the center and begins to fall. So let me show you now how we can just take those prelims and put them into a trig graph. Now tradition has been that Ferris wheels are like the problem of choice. I don't know if that's going to be the case because you guys are the first people doing the new Math 12. But we'll try some other kinds, but we'll start with the Ferris wheel here. This says a Ferris wheel has a radius of 42 meters and its center is 43 meters above the ground, and it rotates once every 50 seconds. Let's graph what it looks like then to begin with. So if you're on the Ferris wheel and you start at the bottom at time 0, okay, then how high above the ground do you think you are? Can be hard to do without a picture, right? 1 meter is correct because the Ferris wheel is a radius of 42, but it says it's 43 above the ground. So that means it's out of proportion here, but it wouldn't fit for me to write it in. That there's 1 meter when you get on, right? You don't want to ride a Ferris wheel, by the way, that is at 0 on the ground, because that means you're going to get mangled as it comes back down to the ground. It's just going to, yeah. So this is 1 meter above the ground. So we're not really going to make a super accurate sketch here, but we'll just show that by putting it above the axes. Okay. Now, somebody tell me, where will you be? Pick a time and a height. Can you figure out a time and a height where you're going to be? So close. Yeah. This is the point on the Ferris wheel where you're going whee, right at the very top. And how long does it take to get there? Well, half of a turn. So let's just say this is, let's call this part here 25 seconds. That means this will be 50, 75, 100. So at 25 seconds, you'll be at the top. And again, if you're not sure how far it is or how some of your classmates figured it out, there's 42 meters to get the rest of the way. So that's 84 is the length of the the diameter of the Ferris wheel, and 1 meter above the ground. So now you're 85 meters. And then at 25, let's put it up here, and we'll say that that's 85 meters. Okay. Can anybody pick another time and a height?
50 and 1.
Yeah, 50 and 1, that works. Any others? 75, 85, okay. Nobody wants to be brave yet? Okay, here, I'll take the next one from you. 101. You should be able to tell me how high this person is at 12 and a half seconds. How'd you know that? You're correct.
Because it's only now, and the radius is, well, it's, I don't know.
That's all right.
I can't explain.
If you think about it like pizza again, Ferris wheel pizza. This is a quarter of the circle. That Ferris wheel is spinning at 50 seconds to get all the way around. 12 and a half seconds is 1/4 of the 50 seconds. So that's how you know you're going to end up right there at the middle of it. And that's a height of 43. So it'll be somewhere like this. So if you were to picture this rider getting on, and let's say they rotated like this till 12 and a half seconds, 25 seconds, 37 and a half seconds, right? They're doing what you've already been doing on the graph. They're going from minimum to center to maximum to center to minimum to center to maximum to center to minimum. They're bouncing up and down like a trig graph. Okay. So it would roughly look like this as we plot it out. So, you know, like if James Bond had a target on a Ferris wheel, he could calculate what time and what height and where they would be so he would know when to get them. I don't know another practical use for this for you other than like maybe if you're taking pictures of your friends at the P&E this summer and you're like, okay, wait a second, at 37 seconds they'll be in view, take the picture. Anyway, but this is trying to illustrate to you that it is a repeating, the Ferris wheel repeats, right? It keeps circling round and round. So can we come up with an equation for it? What are the normal things we want in a trig graph when we come up with an equation? Just what are some of the things you're looking for? I don't want numbers, I just terminology. What am I looking for? Amplitude, period. Okay, so let's start listing these things. What's the amplitude of this graph? Sorry? How much does it go above and below the center line? Forget you're looking at a Ferris wheel. 42, yeah. It can only go up by the radius and down by the radius. So it's 42 is the amplitude. The period. How often does this Ferris wheel repeat? Yeah, every 50 seconds. All right. What about a center? Do we know where the center line is? Very close. 43, yeah. It goes 42 above 43 and 42 below 43. Then finally, we need a phase shift, right? So we have a phase shift. How can we come up with a phase shift? We were just doing this like yesterday. We gave you a graph and you came up with the equation. Well, here's the graph that we plotted. You could do that, right? And the reason I said it's advantageous to think a step ahead is if this were me, I'd be picking that point there. What's the phase shift on that big black dot? Zero, right? I haven't moved that graph left or right. Where it is at 0. That's my favorite spot to pick. So I'm going to try to come up with an equation that doesn't have any phase shift in it. So I have to use negative cos x. That's this graph in the black dashed line, negative cos x. If I do it from that point of view, I don't need to worry about the phase shift. It's right there where I started the problem. You know, if you like to make life harder for yourself, you could go like this and tell yourself, oh, well, this green one, this is still correct. You're going to get all your answers right. But this green dashed line is a positive cosine graph. Now you got to figure out it's been shifted 25 units to the right. So it still works that way, but it's to your advantage to try and think, you know, of your choices, which one will make it simplest. Yeah.
Why not use sine?
You can use sine, of course you can. This is one spot where I would pick for the sine graph because this purple graph here, it's like we went on the roller coaster and someone got sick. Look at all the colors. That purple graph is the sine, which has been shifted right by 12.5. So none of those are incorrect. I'm just telling you that by choosing negative cos, I have no phase shift to add to my equation. That's all. So this time, let's go and put it all together. If I wanted an equation for it, this is the one I'm using negative cosine. So that purple equation there will satisfy this rider who's going on the Ferris wheel. And yes, you could reduce your fraction to pi over 25. Of course, you can do that. So how high do you think that that person would be at 65 seconds? So let's use our model to predict that. We don't have to take a guess here. We can actually tell you exactly what it is. So I'm just going to show you one thing in your calculator that will make life a lot easier for you. So you're going to want to follow me here. It'll definitely help you as you're doing these kinds of questions. We're going to put our model into the graph. So we're all going to type in negative 42 cosine of, I'll write it in as pi over 25. That's the reduced fraction. And then my center line is 43. So right now, I could verify what this graph looks like. I better make sure I'm in radian mode. Yeah, okay. But if I want to see a nice trig graph, we definitely want to make sure the window is a nice one to look at. So what do you think? For this window, what would it make sense for my x minimum to be? Yeah, 0 makes a lot of sense because that's when we get on the roller coaster, right? Now, should I leave it at 10? Like, does that make sense? Should I stop at time 10? Yeah, don't get off the ride 10 seconds in. That's a problem. How long do you think I should let it go? Well, our picture there is 100. If all I want to see is one cycle of it, how long should I let it go? 50, yeah. Everything after that is just repeating the same information back to me, right? And you're going to get a lot of tick marks here, so I'd probably pick something like 5 or 10 just so you don't have all those, your axes all cluttered up. Okay, what makes sense now for a y minimum? Yeah, 0. Some people say 1. That's fine too, right? But we want to see a whole picture of the Ferris wheel. And then the maximum, what do you think? Where should I stop? 85, yeah. So you could even go higher. Like, there's nothing wrong with saying 100. But again, this is going to show me a nice window. Let's see. Ready? You ready? Whee! There, okay. So as you hit the top, that's the picture of this graph is actually going to look like to you. Okay? Let's go and calculate our estimate. So I'm going to show you now how to substitute in on this calculator. You probably don't know how to do this yet, so you definitely want to try along with me. What I'm going to do is I'm going to clear the graph, go back to where I started, and you see this button here that says variables. You're going to click on variables. And we're interested in y variables because the y variables, they come from back here. See, y1, y2, y3, y4. So variables, y variables, and it's a function that I want, because we've already entered the function, it's y1. So if I go y1, uh-oh, whoops, I put it in the wrong spot, my apologies. And it was going so well. So my original problem was that I was in the wrong screen. You should be on this screen where you can do calculations. You guys probably are, because I meddled around with mine to show you something. But now that you have y1, if you put your brackets in, it's just like any other function that you've worked with. That's like saying substitute 65 in for that function. So when I hit enter, it does all of those calculations in for you. So it doesn't save you time if you're only going to calculate something once, because you have to do all the same amount of work to calculate it once. But if you're going to do it a couple of times, this means the next time I want to know, I can just go, what is y1 of, I don't know, what time do people want to learn about? Anyone have a favorite number? No favorites or lucky numbers? Nothing? All right, 71 it is. At 71, you would be 79 feet, or sorry, meters, I guess. 79 meters above the ground, 79.8. All right. So our original, we were asking about 65 seconds, so it'll be 55.9, we'll call it 56. 56 meters is what it rounds to. Now, this first time, I'm going to show you how to do it algebraically. The next time, we'll work it out with the graphing calculator, which is also going to be something new for you. So if I want the height to be 25 meters, there's a better way of writing this, y equals negative 42 cosine of 2 pi over 50x. Like, that's okay, but generally, you're going to see it written like this. The height as a function of time. It's the exact same equation. It's just maybe a little more descriptive if we write it as the height as a function of time. Because then if you give me a height of 25 meters, that's going to go right here. And I'm going to try and figure out what time it was. So this is what I'm going to set up, is 25. Where is that equal to negative 42 cosine 2 pi over 50 t plus 43. So let's start rearranging it. I'm not sure if you're going to get stuck at one point here, but I'll walk with you as we do it. So I think that's going to be 18. Sorry, negative 18. And negative 18 over negative 42. I guess I can go one more time here. That'd be 3 out of 7 if I simplify that fraction. I might as well simplify this one too. Okay, so at this point you might be like, I don't know what to do now though, because I can't get the t out of cosine. Does anybody know how you pull it out or how you rewrite this? Has anybody seen this before? Yeah, you have actually seen it. It's just you've probably never used it in this context before. So if I want to reverse this, this is my y and this is my, let me write it in a different color here. This is my y and this is my x. So if you want to get them to switch places, you got to use the inverse, right? So what I'll do is I'll rewrite this then. This would be the cosine inverse of 3 out of 7 equals pi over 25t. Now they switched places, so I can rewrite it and solve for the time. So it'll be 25 inverse cos 3 over 7 divided by pi is equal to t. So I get about 9 seconds. So we'll call it 8.98 seconds. So the good news for you as we get, one thing at least you'll start to appreciate when we get to calculus is they know life's hard enough for you, and they'll just let you use your calculator for this every time. You won't have to do it by hand because, you know, they don't want you to fumble on something like this when we're doing some difficult stuff. I don't know why anyone would want to do it by hand. We'll try it again here. I'll show you how you can use your calculator for it, okay? I mean, why anyone would want to do it by hand except maybe to pass a test. Okay, so this time we're going to look at the tides, right? The tides are something that repeats every day. Here's the fact that's going to blow your mind that the first time I heard it in physics class when I was in university, I was like, no, you're lying. Our professor said that the Earth is going to stop spinning one day, and you can calculate where it's going to be when it stops. Anybody figure out why the Earth's going to stop spinning according to him? Well, the moon is what pulls the ocean across back and forth, right? Every day with the tides. Yeah? So every time the moon pulls the ocean back and forth, there's a bit of friction between the water and the Earth, right? So every time it's going, it's actually losing some energy as the Earth spins. So I don't know when it's going to be, but make sure you buy your real estate on the sunny side of the Earth for whenever that happens. Okay, I'm sure, or at least tell your relatives that inherit your estate to buy it on the sunny side. Okay, so this time we have a maximum depth of 15 meters at 7 in the morning and a minimum of 5 meters at 1:30. Okay, so we want to write the equation for the depth of water versus time. So you can think about it like every other graph we've looked at. We need, what are the pieces? You start shouting them out to me. What do I need to find? Amplitude, yeah, what else? Period, what else? Center I heard, and phase shift I heard. Okay, so can anybody figure out one of those pieces by looking at that stuff? No. Yeah, of course you can. These ones even have a nice little formula. Amplitude? What's the amplitude going to be? 5? Yeah, it's going to be 5. The distance here is 10, right? 15 minus 5 divided by 2. That's 10 over 2. So it's going to bob up and down by 5 meters. What else? How do you get the center line from that information? How do you get in the middle of the minimum and the maximum? You add them and divide by 2. So maximum plus minimum divided by 2. 15 plus 5 divided by 2. So we're 20 over 2. The center line is 10. And that should make sense when you look at the problem. The tides at middle is 10 meters, the depth, and it goes as high as 15. That's an amplitude of 5 above, and as low as 5, an amplitude 4 below. Okay, can we come up with a period from the information we have? Very close. Here's what you have. You have a maximum depth, and you have a minimum depth. This is 7 a.m. till 1:30. So this is one of those things where those European clocks kind of make sense, right? 24-hour time. 13:30, that's 1:30. I guess you don't need PM when you write 13:30. That's 6.5 hours, right? So 6.5 hours has gone by in this picture here. So what we need is the whole thing though, right? Yeah, so the period is actually going to be 13. Now, where did this graph start? Minimum, maximum, center?
7.
It starts at a maximum at 7 a.m. So that means this graph has been moved to the right. It doesn't start at 0 anymore. It starts at 7 a.m. So it's been moved 7 to the right. And what graph starts on its maximum? You have cosine, you have sine, you have negative cosine, you have negative sine. Yeah, cosine starts at its maximum, and in this case, that maximum starts 7 to the right. So here's 7 a.m., which means I've shifted the cosine graph 7 units. And again, it's not wrong for you to pick a different model, but I don't know why you would. The other one that makes sense to use here, if you were wondering, it makes sense also to look at the minimum, and you could shift the graph based on where the minimum is, because you've got that information. The minimum happens at 130. That means you've shifted it to the right by 13.5, and that would be a negative cosine graph if it starts at the minimum. Okay. So this one we're gonna stick with the maximum, which is 5 to the right, and the graph we're using is cos x. So if I put all those pieces together, I have, I guess we'll call it, oh sorry, 7, thank you. So we'll call it the depth as a function of time is going to be 5 cosine 2 pi over 13. We move it 7 units to the right, because that's 7 o'clock in the morning, and the center line is 10. All right, so let's use the calculator again. I want you to enter that in. We're going to work with that function, so I'll pause the video because you don't need to see me entering it in, but put that in now as your y1 equation. So it should look something like this when you've entered it in. What can we do for a window here? We want to make sure we see a nice picture. So what should we do if we're going to look at this? It doesn't have to be exactly lined up, right? You just need to be able to reason with why it makes sense to do what you're doing, right? If we start at midnight, like if we look at our problem, it wants to know 11 a.m., so we definitely have to go at least that far to get some idea. But, you know, let's go from 0 to, why don't we go 24 hours? We'll see what the tide has done in one day. Knowing that the period is 13 hours, right? I could also say to myself, that's going to show me 2 cycles of it. That goes just a little further than a day. That makes sense too, right? But in this case, we don't need that much of the graph, so no problem. But we do need, it has a minimum depth of 5, so I'll see it. 0 is lower than my minimum, but I'm still going to be able to see the whole graph. And now 85 doesn't make much sense because the graph will be shrunk so small if I use that, right? I can stop at 15. I know it doesn't go any higher. I don't know, I'll pick something like 3 here. So here's a picture of the tide. And remember, mine's going to show you 2 cycles because I went for 26 hours. Okay. So the first thing we want to estimate is we want to estimate where is the, what's the depth of the water at 11 a.m. So we're going to clear the graph, and we're going to use that function. So I'm going to go variables, y variables, and I want to know where is this at 11 a.m. So the tide is 8.23 meters deep. Now, I don't know if you knew that your calculator could do some tricky solving stuff in there. There is a reason that they cost so much money, but we're going to get the calculator to do the work this time. We're not going to do it by hand. This time it says a cargo ship needs 8 meters of depth in order to get in and out of the harbor. So we want to know how long can they be in port before they have to get out, before this thing beaches itself, right? So I'm going to show you on a picture so we can talk about it. This is going to show me the tide, right? What I want to add to it is, where is 8 meters? Because now I can tell you, well, if you want that boat to safely be in port, it better happen when it's above 8 meters, somewhere in this area here. It's a problem if your boat is in port right there. Okay, it's below 8 meters. So we're trying to figure out, how long do I have from when right there, they'll say, okay, come on in, and I can bring the boat in, and then I have to be out of the port by the time I get back to there. Okay? So what we need to know is what is this time, right? What time can I come in? What time do I have to get out? And then I'll know how much time I have to spend in port. So here's the way you do it in the graphing calculator. I'm going to show you two ways. So the first way is the intersection method. So you see this calculate? You're going to calculate the intersect. And it's going to ask you, you see this little crosshairs? You're going to move it to where you think that you want to see it. So I'm going to move this all the way to the first time. Don't worry if you missed it the first time. I'm going to do it again for the second point. And this is about where I want the first curve to be. And the second curve. And then it's going to ask me for a guess. Most of the time, you're just going to hit enter on all three of those. You'll learn a little more in calculus about why it is the calculator asks you for that those points. But for now, it's going to tell me that at 2.89, well, I guess 2.90 when we round, that's the first time the depth hits 8. And that's what you can see here is the depth is 8 at time 2.9. Okay, so the first time is at 2.9 seconds. And we're going to do the second time here now. Sorry, not 2.9 seconds. It's 2.9 hours, right? It's a pretty fast-moving tide. So let's calculate it again. So if you missed it the first time, watch me as I go. I'm going to hit the second button, second function, and I'm going to calculate. That's the trace button. So hit trace, and you go to this screen. Hands up if this screen is in front of you. You want to see it again? So it goes second function, and you hit the trace button, and you should see this menu in front of you. Intersect is 5. That's the one we're going to. You can hit the number 5, or you can move it down and press enter. Both work. You're going to move it along the first curve. So I'll move it until I get to somewhere close. Question, yeah? Oh, this horizontal line here? We added 8 meters to the problem so we could see 8 meters in our window. Oh no, and I lost that. Okay, so calculate intersection. So first curve and the second curve. And then I'll put it on a good guess. So what is it? That time is 11.1 hours. The next time when it hits the 8 meter. So if I wanted to tell you what the difference in the two times is, I just have to subtract them. So I'm going to go to clear my graph. So now I can work with my calculator again. You can type them in, or whatever the last thing the calculator found out for you, it's always stored here. You can go second function, answer, and it's that 11.1 second we just had. So if you ever need to get the number back and you don't want to write all the decimals down, that's how you do it. We'll take away the 2.9 seconds we had before. So it'll be about 8.2 hours. $8.2 hours for the boat to get in, get loaded, and get out. So this one I'm going to have you try and run it on your own for a bit, and then I'll review it for you, but I'm going to give you some time to work ahead here. So this time you're looking at hours of daylight, and these are the days of the year. So this is the day, and this is hours. So your job is to try and come up with a model here. Now, you can use any of the points you want in here, but there are some very, very key points that you're going to want to use. Notice what kind of information we got. It doesn't give you some random like, oh, it's a depth of 7 meters at 9:30. That doesn't help us as much in the problem. What do you think the most key points we're always looking for are? Well, first and last, but you probably think of them as a different minimums and maximums, right? You want those extreme ends of the problem. So take a look here and see if you can come up with a model to explain how the daylight would move in Windsor, Ontario. So there's some good discussion happening out there. I'm just going to try to catch up. Hopefully you've had some success there. No? So if you look through your data here, you're looking for a minimum and a maximum to work with. The largest is going to be there. And day 172 in a 365, that's like about June 21st or 2nd, whatever the summer solstice, I think is what it's called, is. And then the minimum here is 9.08. That's like probably December 22nd or whatever. You know, like where up here in Canada we get like 5 hours of sunshine that day, and it's like you wake up and it's dark, you go to school and you don't get to see the outside, and then when you leave school it's still dark out. Yikes. So here's my minimum, my maximum. I also have, I know how much time went between them. So if I have 355 and 172, how many days happened in the middle there? Lots? 183? Which if you actually, that's half of a year, right? Between the shortest and the longest day. So 183 days from the maximum to the minimum. So let's start putting together some pieces. We should be able to tell me at least these things by now. Amplitude, period, center, and I think you can probably even come up with the phase shift. But let's start. You pick. Let's do that one last. I usually always do that one last. It's the hardest. It's easier to talk about it once the rest of it's there. Period? Okay. So if the distance from the maximum to the minimum is 183, that's only half the period, right? That's only half of the graph. I went from the longest day down to the shortest, so I got to double it in order to get the rest of it. So the period in this case is 366, aka a leap year. What's the amplitude going to be? 3.1? Okay. So if you were to go 15.28 minus 9.08 divided by 2, you get 6.2, which gives me an amplitude of 3.1. Okay? That's the distance from maximum to minimum. Amplitude is half of that. Okay, what about a center line? So some people are starting to get a hang of it here. 9.08, and then we divide it by 2. If you want to end up in the middle, you add them together and divide by 2. So sorry, what was the middle? What did it turn out to be? 12.18. Yep. Okay. Now the phase shift here, it depends on your perspective of when you think about this problem. I'm going to do it from the point of view of this one right here. This one here is the maximum. So what graph do I have that starts at a maximum? Right, the cosine is the nice one to work with. This graph does not start at 0. Where does it start? 172 to the right. So one equation that I could use is y equals 3.1 cosine 2 pi over 366 x minus 172, and the center line is at 12.18. Okay, so that means we can go and plug it in the calculator to find out what it would be on March 10th. But now this is the only annoying thing about calendar dates. So March 10th, does anybody know what day of the year that falls under? It's your birthday? No. No? You just like giving some attention, huh? So January, you do that 30 days, have November, April, June, and September. So January has 31. Then February, I guess in this one we have to assume that it's, let's just say 28 for simplicity. I think it has 29 because it's a leap. We'll keep it simple, okay? We'll keep it simple. That means when I start out at March, I've already gone through 59 days. And then 10 more because it's March 10th. It's the 69th day of the year. So let's plug it in. I'm only using it one time. I'm not going to go through all that stuff in the calculator that I did last time. I'm just going to plug it in. So 3.1 times the cosine of 2 pi over 366, and the day is the 69th, minus 172, and my center is 12.8, 18, sorry. So that day, March 10th, should have about 11.57 hours. So something new for this year is we're now doing tangent applications too. So let me show you what one of those might look like. If you've got a plane and it's flying towards you, super fast. This plane's flying and you're here on the ground. And we have 5,000 meters where the plane is altitude. And there's this angle between you and the plane there. So this is the horizontal distance. I'll call it h for horizontal. I can come up with a function here to describe where the plane is, or the horizontal distance there that's left over, using tangent. And that's that the tangent of theta is the opposite over the adjacent. So I have a function then that height is 5,000 tangent of theta. So if you can measure the angle between you and the plane, you know the horizontal distance between you. Now, I'm going to just show you what this graph would look like. Okay, so in this case, if you think about how does the function relate to the problem, this is pi over 2, or 90 degrees, and this one here corresponds with negative 90. So if you think about what would it mean then for the if the distance got all the way so that there was a 90-degree angle, what would that mean? If they're directly above you, the angle would be 0, right? So directly above you, the angle would be 0, which if we could zoom in here, well, the horizontal distance would be 0 as well. But if you think about it at 90 degrees, the only way, like every time that plane gets further away, that angle gets a little bit larger. So the only way that you can get 90 degrees, is if the plane went all the way off to infinity. You just kept pulling that line longer and longer. It's not possible, right? Which is why you see it hug the asymptote in the picture like that. Because the only way you're actually going to see a 90-degree angle is if that plane was literally all the way flying off to infinity. So don't get on that airline. Okay, and then the other way, it's negative because it's going away from you, right? It's the other side of the graph.